welcome to another session of QBA Clips. In this session, we're going to talk about the Poisson and exponential distributions, two additional probability distributions that are another example of a discrete distribution and a continuous distribution. These two have a particularly unique relationship to each other, as we'll see. So let's proceed to talk about both of these distributions. We spent time talking about the normal and binomial distributions at considerable length. And again, the binomial distribution is an example of a discrete probability distribution. The normal distribution is a continuous probability distribution. Well, we're going to see one more example of each of those, and you'll recall, hopefully, that there's a difference in the way we manipulate the formulas in Excel for the binomial and normal distributions that have to do with the fact that the normal distribution is continuous. But we'll see that difference pop up again as we look at these two distributions in this QBA clip. All right, well, let's dig into the Poisson distribution. And like all of these probability distributions that we're dealing with, they are families of distributions that are defined by specific parameters. You remember the binomial distribution was specified by the number of trials on the probability of success, n and p. Normal distribution was exactly specified by the mean, mu, and the standard deviation, sigma. Well, the Poisson distribution is uniquely specified by one particular parameter. In this case, it's a parameter called lambda. But it's a discrete distribution, and it applies in specific circumstances where you're looking at the distribution of counts of events, number of events happening in a unit time or unit distance, unit space. It's some discrete events happening over some interval of, actually an interval of some continuous variable, as it turns out, time, distance, space, etc. And some examples might be the best way to illustrate that. Number of customers arriving per hour. We looked, I think, earlier in the term at bank arrivals, right? Inter-arrival time. So here, not inter-arrival time, but now a count of number of customers arriving per hour. Number of defects per square foot in some paint job. Number of device failures in a month. These are all examples of variables, of discrete variables, number of customers, number of defects, number of devices, that could be modeled using the Poisson distribution. And as I said, this distribution is characterized by a single parameter. And it's a parameter called lambda, which is always positive, and that's the rate. That's the rate of arrivals of customers, for example, rate of defects per square foot. And it's a rate in a given specific unit, as we'll see. So rate of arrivals per hour, rate of failures per month, rate of defects per square foot. All of these would be the lambda. And that's kind of the average long-term rate taken over again, a long period of time. Lambda, as it turns out from the mathematics of this Poisson distribution, represents both the mean, right? It's a long-term average rate of arrival, and also the variance of the distribution, so that the standard deviation is given by the square root of lambda. So from lambda, we derive both the mean and the standard deviation of the distribution, of the Poisson distribution. All right, well, let's see how we would get this to work. And we can do this looking at an example of calls coming into a call center or a help desk. And supposing we had calls that arrive into this help desk according to some Poisson distribution with a lambda equals 5 calls per 15-minute period. So on average, we get 5 calls coming in per 15-minute period. And you could think of that in minutes, or you could convert that to hours. So 5 calls are coming in any 15-minute period, and you have 20 calls coming in per hour. We can calculate the probabilities associated with various numbers of calls coming into the help desk using this formula in Excel, where the formula, the probability of associated with k calls coming in per hour, let's say, would be equals Poisson. Then you have three parameters: k, the value of the variable you're interested in; lambda, the rate; and then you have the cumulative flag that you're going to either turn on or off, just like in the case of the binomial distribution. Because since this is discrete, you can calculate the probability of having exactly a certain number of calls coming in per hour. Now, one of the things that's very important is the units have to match up between lambda and your value k. So if I want to know the probability of 5 calls coming in per hour, then I need to make sure I'm expressing my lambda in calls per hour. I can't put it in as 5, number of calls coming in per 15 minutes. So the k value and the lambda have to match up in units. But of course, lambda is scalable, so you can express lambda in minutes, in calls coming in per 15 minutes, or calls coming in per hour, calls coming in per 1 minute, calls per day, anything of that sort. You can just scale a lambda up and down as needed to match your variable k. Well, let's take a look at some numbers, some probabilities that we can calculate from this distribution for this help desk example. So we have calls coming in, let's say, to the Rollins help desk over at the library. And the mean of this distribution, the lambda, is 20 calls per hour. So you notice I've expressed this in calls per hour. And part A asks here, what's the probability that exactly 10 calls come in per hour, or in a given hour? Okay, so we can think back to our formula. Equals Poisson of, I want to know exactly 10, so 10 will be my k. My lambda will be 20 calls per hour, so the units of k and lambda have to match up. And in this case, I have to decide, do I want my cumulative flag turned on or off? And if you're recalling from our discussions on the binomial distribution, if I want the probability of exactly 10 calls coming in, then I certainly don't want the cumulative probability, so I'll have that cumulative flag turned off. Let's see. So equals Poisson, P-O-I-S-S-O-N, my value of k, or x, which will be 10 in this case, comma, lambda 20, comma, 0. So I get a probability of 0.0058. What about the probability that 5 or more calls come in per hour, so greater than or equal to 5? Again, we've exercised manipulating these formulas quite a bit, so we should be pretty certain of what we need to do here. I want 5 or more, so I'm going to have to start out saying equals 1 minus, I have a greater than sign in there, say 1 minus Poisson of. And now I have to think, do I want to include 5 in the part that I'm subtracting, or do I want to keep it in the part that I'm retaining? I want 5 or more, greater than or equal to 5, so I can't subtract the probability of getting 5 from 1 here. So I have to step down from 5 to 4 and say 1 minus Poisson of 4, comma, lambda, comma, 1 in this case. I need that cumulative flag turned on. Okay? And I'll add some, it looks like a probability of 1, but I'll add a few decimal places. So again, if the average is 20 calls per hour, the probability of getting 5 or more calls is quite high, very close to a probability of 1. All right, then the next part asks the probability of having less than or equal to 25 calls coming in per hour. Okay, less than or equal to 25. In this case, would I start with 1 minus or just Poisson? Well, since it's less than, I know the Poisson formula is going to give me that, so I'll say equals Poisson of 25, comma, 20, comma, 1. And in this case, I didn't have to step down from 25 to 24 because I wanted 25 included in my result. Okay, supposing I want to know the probability of having somewhere between 10 and 30 calls arriving in a given hour. And here I say inclusive. And what does that mean? Well, I want the probability of getting between 10 and 30 calls, including those two boundaries. So the smallest value I want to include is 10. Largest value I want to include is 30. I don't want anything that's below 10, and I don't want anything that's greater than 30. How would I approach this? Well, there's a number of ways you can, twist this around in your head for sure, but the easiest way is very similar to what we did when we had a probability of being greater than any value. We start out with 1 and we subtract the part we don't need. Well, here, I don't need to start out with 1, but I'm going to start out with the larger value. And say, well, what's the probability of getting 30 or less? And then I'm going to subtract away the part that's below 10. And that'll leave me with the probability of being between 10 and 30 inclusive. So we're going to connect two different Poisson formulas here. Equals Poisson of 30, lambda, 1. Not done yet, but this piece gives me everything 30 and below. So 30 all the way down to 0 calls per hour. But I don't need all of that. I want to subtract part of that. And I'm going to subtract from that the probability Poisson of what? Now this is the part that we've got to think about. If I want to make sure I'm retaining 10 and 30 in this probability, well, 30 is covered by this first portion of this first Poisson formula. The second one, though, if I want to make sure I'm not subtracting away the probability of getting 10, then 10 cannot be in this piece that I'm subtracting, so I'm going to have to subtract Poisson of 9, 20, 1. And that's an interesting formula that sometimes takes a little bit to get our heads around, but if you think about what the formula is doing, then it'll make sense. I'm starting out with a probability of getting getting 30 or below, and then I'm going to subtract the part I don't want. Well, the part I do want starts at 10, so I can't subtract 10. I have to start out by the piece I'm going to subtract is going to start at 9 and everything below. Okay, now as a slight variation of that, we could ask what's the probability of getting between 10 and 30 exclusive of those boundary values. So now I don't want to include 10 and 30. I want to include everything from 11 up to 29. So I'm excluding the values of 10 and 30. How would that change the formula that we just developed? Well, the upper end of the probability range, the value range I'm interested in, is not going to be 30 anymore. It's going to be 29. So I'll start out with Poisson of 29, 20, 1. And then what am I going to subtract? Well, in this case, I no longer want 10 retained in the probabilities I'm keeping. So I'll now subtract Poisson of 10, 20, 1. So let's see. Let's plug that in and see what we get. So we get Poisson of, if I'm excluding 30, then my highest value I'm interested in is 29, 20, 1, minus the pieces on the low end that I don't want. And if I'm excluding 10 this time, then 10 is going to be the highest value that I don't want. So Poisson of 10, 20, 1. All right, and as you'd expect, the probabilities, excluding the values of 10 and 30, are going to be smaller than the probabilities including the values of 10 and 30. And the difference between them, this inclusive value and this exclusive value, of course, should be exactly the probability of getting exactly 10 plus the probability of getting exactly 30. Right? That should make sense. Okay, then let's just take a look at one more problem, very similar to something we looked at for the binomial distribution. What's the largest number of calls, k, such that the probability of being greater than k is at least 95%? All right, so we just have to get our head around this. We know if we start out, say, what's the probability of getting anything greater than 0 calls? The average is 20 calls per hour. Well, that probability is going to be very, very large. So very close to 1. What about the probability of getting 5 or more calls? Or let's say greater than 4 calls. We have that number up here. 5 or more is the same as greater than 4. And that's 0.999983. Okay, so still very, very large. Not quite as large as the probability of getting greater than 0 calls, but still pretty large. So we see the trend here. As k increases, the probability of having a number greater than k decreases. We want to know what's the largest value for which, largest value of k for which the probability of being greater than k is still above 95%, right? So we're just going to, one way to do this is just trial and error. In fact, the only approach we'll cover here is to do trial and error. We can plug in a certain value, and we're just going to create a formula that says what's the probability of being greater than k. So let's just put in 4 as our trial value. So the probability of being greater than 4, we just need a formula that expresses that. So we'll say equals, and again, if we think about this, probability of being greater than 4, I have to start with a 1 minus Poisson of what? Drum roll. Well, the question is, what do I want to subtract away? Well, it's greater than 4, not greater than or equal to 4. So the part that I'm subtracting away is going to include 4, comma, 20, comma, 1. Okay, and I picked 4 in this specific case just to show you that we'd get exactly the same answer that we calculated above for the probability of being greater than or equal to 5. Okay, all right, so greater than or equal to 5 is the same as saying greater than 4 in the case of a discrete distribution. All right, well, this number is way above 0.95, so all we're going to do is just try different values of k until we see the number drop below 0.95. Okay, so we can just keep doing that by trial and error, or we can do it. We can display the trial and error results in a data table. I think we've gone over this in class, but I'll show you how that would work. What I've done is I've laid out a data table in such a way that I'm going to try these values of k from 0 down to 19, and beside them I want Excel to display what the result would be, the probability of being greater than k. So I've, in my little formula spot in my data table, I've just linked to the formula that we just created. Okay? And now I'll build this in Excel. So I'm going to select both columns and all the rows, including the row up the very top row, right, where my blank cell is and my formula. I'm going to go under Data, and again, remember we showed this very briefly in class, and I actually there's another QBA clip that'll focus on data tables as well, but the layout of this data table is very important. I'll go to Data, What If Analysis, Data Tables, and in this case my trial values are in a column. And where do I want to input each of these trial values? Well, right up into the cell where I was putting my trial values before, which in my case is going to be B19. I hit OK. Cell thinks for a while and generates all these probabilities of being greater than each of my trial values. And as we go down the list, we get to, it looks like 12 would be the largest value of k for which the probability of being greater than k is above 95%. Any larger values of k and that probability drops below 95%. Okay. One last thing I wanted to cover on this Poisson distribution is just how we can scale the lambda or the rate. So this last extra problem, as I call it, says, well, what's the probability of getting over 100 calls in a 4-hour shift? Okay. Now, so far we've been working with lambda in calls per hour, but here we're going to scale this up now to a 4-hour shift. So if I get 20 calls coming in per hour, then I really have 80 calls coming in a 4-hour shift as my lambda on the average. I want to know what's the probability of getting greater than or equal to 100 calls in a 4-hour shift. So that should be easy. I have greater than, so I'll say equals 1 minus Poisson of, and here's what I have to where I have to think now. I want greater than or equal to 100, so am I subtracting from 100 down? No, I'm only going to subtract from 99 down, comma, lambda, but lambda is going to be now the lambda across the whole 4-hour shift, not 20, 80, comma, 1. Okay, so if I'm dealing in calls per hour, I use the lambda appropriate for, for a 1-hour time interval, which is 20 calls per hour. But if I'm looking at a value across a 4-hour shift, I have to remember to multiply that by 4, so I get 99, 80, 1. Okay, so let's exercise a number of things on our Poisson distribution. Let's dig into this problem a little bit more. Before we leave, I just want to make sure you note the very strong similarities between how we manipulate the Poisson distribution and how we manipulate the binomial distribution in Excel. Okay, here's a question. Supposing this help desk is manned by 2 people, or woman by 2 people, and one of the 2 attendants on duty, this one, a man, realizes that he forgot his cell phone in the men's room 2 flights up in the next building. Now he wants to get that cell phone back quickly because there's, who knows, maybe there's some incriminating evidence on that phone that he doesn't want to fall into the wrong hands, or maybe he just doesn't want people making, somebody grabbing his phone and falling all over the world and running up his bill. Either way, he wants to get that phone back as quickly as he can. It'll take him exactly 2 minutes each way to get up to the men's room in the next building over, 2 flights up, get there and back. 2 minutes each way. So, a call has just come in that his teammate has picked up. Question is, what's the probability that he can get his phone and get back before the next call comes in? So what are we asking ourselves here? What's the probability that the next call is going to take at least 4 minutes before it comes in, right? 2 minutes each way. That's the only way he can get to his phone and back before the next call comes in. Right? And then we could also ask, what's the probability that the next call might come in before he even gets to the men's room? So in less than 2 minutes. And here now we're talking about something a little bit different. We're talking about the probabilities not of a number of calls coming in per hour, but we're really investigating that interval, that continuous interval of time in between the calls that are coming in. All right? And it turns out that this group of questions can be answered by the exponential distribution. The exponential distribution is a continuous probability distribution, and it is directly related to the Poisson distribution in that if we have a number of events per unit time that are governed by the Poisson distribution, then the probabilities associated with the intervals of time in between events will be described by the exponential distribution. The variable, like I said now, is this continuous interval of time or distance or what have you between events. So again, we're talking about just 2 sides of the same coin, if you will, not the probabilities of the numbers of events per unit time in this case, but the probabilities of certain time amounts of time elapsing in between events. Now, because these things are so closely related, this exponential distribution is obviously going to be governed by the same parameter. We're still governed by the fact that there are 20 calls on average coming in per hour to this help desk. Okay? And it turns out that that's the same rate, that lambda calls per hour is the same parameter that's used to describe and specify the exponential distribution. So if calls come in with an average of 20 calls per hour, the time in between calls, okay, follows an exponential distribution with the same parameter, lambda equals 20. The average time in between calls is going to be 1 over lambda. Lambda is still the parameter, but the average now is 1 over lambda, or 1 over 20 hours, which is, 3 minutes. Okay, it turns out again from the math that the standard deviation in this case is also going to be equal to 1 over lambda. And in Excel, the formula that we'd use is expondist. And this is now a continuous distribution, so we will manipulate this a lot like we manipulated the normal distribution in Excel, the norm dist function. So we have expondist of x, whatever time value we're interested in, comma lambda, comma 1, where lambda is still in calls per unit time. And of course, that amount of units, the units have to match with the units of x. And that'll give us our cumulative probability. Once again, because it's a continuous distribution, then the idea of having the probability at a specific time, we're going to treat it just like we did for the normal distribution. So the probability of exactly 3 minutes elapsing between calls is going to be identical to 0. That becomes, again, important in how we manipulate the formula. So, off to the men's room. What's the probability our friend can get his cell phone and back before the next call comes in? What we're really asking there is what's the probability that x is greater than or equal to 4 minutes? Okay. Let's go back to our spreadsheet. So we want to know what's the probability that x is greater than or equal to 4 minutes. And again, because it's continuous, that's the same as saying what's the probability of being greater than 4 minutes. Right? So we will say equals, we want greater than, so we're going to say 1 minus expondist of, right, and here again we just have to make sure we match up our units. 4, you can say 4, comma, and what do I need to put in for lambda? Well, I put in 20 for lambda, except that's expressed in 20 calls per hour. So I need to convert that to minutes. So 20 calls per hour is just 20 divided by 60 to convert that to calls per minute. So I can say 20 divided by 60, do that inside my formula, comma, 1. Okay, let's take a look at that, make sure we're clear on what's going on. Probability of being greater than 4 minutes, or again, same in this case is saying greater than or equal to 4 minutes. It's going to be 1 minus expondist of my 4 in minutes, my lambda expressed in calls per minute. So I've taken 20 now and I've divided by 60 to convert it to calls per minute, comma, 1. So there's just over a 25% chance that he will get to his phone and back in time before the next call comes in. And then what about the probability that the next call is going to come in before he even gets to the men's room? In this case, we're saying what's the probability that x is less than 2 minutes, or again, less than or equal to 2 minutes. Thing in this case. Here we just say equals expondist, because we want less than 2, comma, Again, 20 over 60 to convert lambda into calls per minute instead of calls per hour, comma 1. Just under 50% chance. So there's about a 50% chance he won't even get there before the next call comes in. And only a 25% chance that he'd get there and back before the next call comes in. Okay, so hopefully that has illustrated pretty well how we would use these two distributions, Poisson and exponential distributions. And again, they're very applicable to situations where we have a certain discrete event occurring with a frequency over some continuous interval. Time is probably the most common example, but it can be distance or other things as well. And again, those will be governed by the Poisson distribution, and the time elapsed between events occurring will be governed by the exponential distribution. And as we see, we manipulate those in Excel, very much like the binomial and the normal distributions, remembering that the Poisson is a discrete distribution, exponential is continuous.